Hello dear students, how are you all? Welcome to Tejam YouTube channel. In this session, we are going to discuss about all 5-mark derivations from the chapter Electric Charges of Fields, in which we have 5-mark derivations. So 2 based on the electric dipole and 3 based on Gauss law. Okay. So first we will derive the electric field along the axis of the dipole, and second along the equatorial line of the dipole, and then we will move on to applications of Gauss law, where we will derive the expression for electric field due to a uniformly charged infinite straight wire, then infinite plane sheet, then a sphere. Okay. So without delay, let us start. First one, the question will be like this: derive an expression for electric field due to a dipole at a point along its axis. So you can write some theory like, consider an electric dipole of dipole moment P is equal to 2aq. Okay, dipole moment is given by 2aq. Yes or no? Okay, then consider a point capital P or capital X, whatever the point that you want, at a distance small r from the center of the dipole. So you can write like that, and after that you can start deriving. So let me consider a negative charge here. So from here I will derive. I will consider a negative charge here, that is minus q, and there is a positive charge here, that is plus q. Both of them separated by distance 2a. Okay. So I will consider a point P, capital P. This is the small p called dipole moment. Capital P is the point which is at a distance smaller from where? From the dipole center. So from here to here distance is a, and here to here distance is a. From the center to the dipole, from center of the dipole to here distance is r. We need to find out electric field at point P. So due to positive charge, electric field is radially outwards, right? Yes or no? So this will be outwards, A plus. Due to negative charge, electric field is inwards. Okay, sir, why have you drawn E plus bigger and E minus smaller? Because from positive charge to this point, distance is less. How much is that? Till here to here, distance is r minus a. So r minus a is the distance from positive charge to point P. So r minus a lesser. That's why electric field will be more. Due to negative charge, it will be inwards. So direction is okay. But why it is smaller? Because the distance is more. A plus r. R plus a is the distance from negative charge. Okay, na? Now what I will do is I will write the expression for electric field due to positive charge first. Due to positive charge, electric field is 1 over 4 pi epsilon naught q divided by, from here to here distance is r minus a whole square. Okay. In vector form if I write, so I will write it as p cap. What is p cap? P cap is the unit vector in the direction of dipole moment. Dipole moment is directed from, what is this? Negative charge to positive charge. Dipole moment is a vector quantity. So in the direction of electric field, you will get plus p cap. So this is E plus. Similarly, we have E minus is equal to 1 over 4 pi epsilon naught. Here q is there, here minus q is there. Should I write minus q or plus q? Q only, divided by, here to here distance is r plus a whole square. Here to here r plus a whole square. Now sir, here vector is there, p cap. So if you observe, Here p cap is right side or p vector is right side, but E minus is left side. That's why you have to take minus side here. This minus sign is not because charge is negative. Here charge is negative, that's why I have taken minus sign. No. Minus sign I have taken because E minus is opposite to P. You can derive this in a scalar form also, but vector form is standard one. That's why I am deriving it in vector form. Next, what is the net electric field here? Just E plus minus E minus. So total electric field is given by E plus E minus. So E plus is 1 over 4 pi epsilon naught Q divided by R minus A whole square P cap plus this one 1 over 4 pi epsilon naught Q divided by R plus A whole square P cap. Sir, minus is there, sir. Yes, this plus into minus becomes minus. Now E is equal to 1 by 4 pi epsilon naught Q is common, 1 divided by 4 pi epsilon naught into Q is common, remaining 1 by R minus A whole square minus plus into minus minus 1 divided by R plus A whole square. Correct now? P cap at the end. So if we solve this further, you will get 1 by 4 pi epsilon naught Q, that is Q divided by 4 pi epsilon naught, because Q into 1 is Q. Cross multiplication, R plus A whole square into 1 is R plus A whole square minus R minus A whole square into 1 is R minus A whole square divided by R plus A into R minus A. R plus A into R minus A. For both of them square is there. I will take square together. So P cap. So let us simplify this. So E is equal to 1 over 4 pi epsilon naught. Okay, here R plus A whole square is there into Q is there, no? Yes, this is Q. So numerator if we solve, this is A square plus B square plus 2RA, that is AB minus is there, within the bracket I will put R square plus A square, A minus B whole square minus 2RA divided by, what is A plus B into A minus B? A square minus B square, that is R square minus A square whole square as it is, whole square as A plus B into A minus B is A square minus B square, correct now? Now here R square get cancelled because minus into plus minus, minus into plus minus, minus into minus plus. So 2RA plus 2RA will come in R square A square minus R square minus A square get cancelled. So we will be having Q divided by 4 pi epsilon naught 2 times 2RA minus into minus plus 2RA is 2 times 2RA, that is 4RA divided by R square minus A square whole square. Sir, P cap is there, sir. Yes, P cap. Okay, na? Now, just a minute. Okay, yeah. So here we have E is equal to 1 over, what is here, what I will do is, I will take 1 over 4 pi epsilon naught 2AQ will write separately, 2AQ, because 2AQ can be written as P, 2AQ, remaining 2R is there, divided by R square minus A square whole square P cap. 2AR is P, yes or no? So this we can write it as 1 over 4 pi epsilon naught small p 2R divided by R square minus A square whole square. So this is your final answer with P cap. Write down, make a note of it. you can pause the video and make a note of it. Okay, so shall I move to the next one? So this is along the axis, okay, along the axial line. Now let us move on to equatorial line. Derive an expression for electric field due to dipole at a point along its equatorial line. Electric field due to an electric dipole at a point along its equatorial line. Equatorial line means from the center perpendicular line. Okay, let me consider positive charge this side or negative charge, whichever you want. So plus q, this is minus q, here minus charge is there. Along the equatorial means here in this direction. At the center, we have to take some height r. So at this particular point, due to positive charge, electric field is radially outwards. Due to negative charge, electric field is radially inwards. Yes or no? So resultant electric field will be in this direction. E resultant. Okay. So let us consider this is theta, this is theta, this is also theta, therefore this one is also theta, because this side is equal to this side. Let me take from here to here, the distance is a, from here to here is also distance is a, therefore this distance will be r square plus a square under the root. So this distance is equal to this distance. So what is this one? Electric field due to positive charge. This one electric field due to negative charge. So we have to add E plus and E minus. To add E plus and E minus, we have to use vector addition laws. So let us take the component of E plus along x axis, that is E plus cos theta. What is component of E minus along x axis? E minus cos theta. So E plus cos theta, E minus cos theta get added. E plus cos theta, E minus cos theta get added. What about perpendicular? E minus sin theta, sorry, E plus sin theta, E minus sin theta, they get cancelled. Along y axis, electric field components get cancelled. You can write a sentence there if you want. Along y axis, E plus sin theta, E minus sin theta, electric field components get cancelled. Okay, then we have to just find the answer for this. So let's consider E plus. E plus formula is what? 1 over 4 pi epsilon naught. Okay, so q plus q divided by this distance square, that is r under the root r square plus a square whole square, whatever the distance, square of it, whatever the distance, square of it. So next we have E minus. E minus also will get the same. See, 1 by 4 pi epsilon naught, just take the magnitude q divided by this distance square. So E minus is also same. E plus is equal to E minus here. Remaining we have cos theta. So what is cos theta? Cos theta is common there. Cos theta is equal to here adjacent by hypotenuse, that is a divided by square root of r square plus a square. This can also be written as a divided by r square plus a square whole power 1 by 2. Here square root get cancelled right now. Now total resultant electric field E resultant is equal to E plus cos theta, that is E plus is, let me write it once again, E plus cos theta plus E minus cos theta. So E resultant is equal to, since E plus is equal to E minus, E plus is equal to E minus, cos theta is equal to cos theta. Can I write 2 times e plus r e minus cos theta? That is equal to 2 times, what is e plus or e minus? Same formula, 1 over 4 pi epsilon naught q divided by r square plus a square into cos theta. Cos theta is a divided by r square plus a square power 1 by 2. Sir, can we write this in vector form? Yes. So if you write this in vector form, okay, here you have to write p cap. What is p cap? Dipole moment. Look at this. Dipole moment is derived from negative charge to positive charge. Yes or no? Negative charge to positive charge. But E resultant is opposite to p cap. So we have to write minus in here. We will get minus value here. So therefore, E resultant in vector form is equal to minus 2aq, I will write separately, 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, 2aq divided by r square plus what is that, a square power 1 plus 1 by 2 is 3 by 2. Here nothing is there, means 1 will be there, 1 plus 1 by 2 is 3 by 2 into p cap. What is 2aq? Since we know that P is equal to 2aq, while writing the theory itself, you must have written it, right? Like, consider an electric dipole of dipole moment P, which is equal to 2aq. Then let a point P, okay, let a point P at a distance small r along the equatorial line, and then after that you will derive this, right? So 2aq is called P, dipole moment. E resultant is equal to 1 over 4 pi epsilon naught p divided by r square plus a square power 3 by 2 into p cap. This is your answer. Write down. These are the two derivations. You can pause the video and write. Okay. Now, let me write the summary of these two derivations. So, electric field due to dipole. So, if you consider along the axis, you will get one formula, and along equatorial you will get another formula. Okay. So this is the dipole, plus minus along axis here or here, along equatorial here or here, like that. So along axis, what do you get? E, let me write it as axis, is equal to 1 over 4 pi epsilon naught 2p divided by r square minus a square power 2pr divided by 2. Okay. So this is the formula you have got. And along the equatorial, EQUAL, right? So 1 over 4 pi epsilon naught p divided by r square plus a square power 3 by 2. In vector form, you will get p cap here. In vector form, you will get minus p cap here. Yes or no? If in case simplification, if r value is so much greater than a here, what we have to do is we have to neglect a. 2a is the dipole length, it will be very small, and square of it it will become very small. So we have to neglect a square, because a square value will be very less, so compared to r. So if you write that E axis is equal to 1 over 4 pi epsilon naught 2pr divided by r square whole square is r power 4. So if you solve this, you will get r power 3 directly I will write into p cap. So p cap into p can be written as p vector also. So here neglect a square, so a square will get neglected, 0, r square, here 2 will get cancelled, only 3 will be there. So E equatorial is equal to minus 1 over 4 pi epsilon naught p divided by r cube. Okay. Now if you compare these two, what is the difference? E axis is equal to, here minus is there, minus, here 2 is there, 2 times E equatorial. Can I write like this? This will be asked for 1 mark in MCQs. Or in scalar form, it is just E axis is equal to 2 times E equatorial. E equatorial. Okay. Now, sir, along axis and along equatorial is done, sir. What if they ask in random point, at random point? Let's consider here there is a dipole. So here along the equatorial, along the axis is done. What if I need to find out electric field here? That will be asked in competitive examinations like NEET and JEE. Okay. So at general point, electric field is given by 1 over 4 pi epsilon naught p divided by r cube as it is into square root of 3 cos square theta plus 1. Okay, this is the formula that you have to use. For example, here there is a dipole moment in this direction, minus to plus, this theta you have to take. So r in the direction of p will give you theta, that theta you have to substitute here, fine. So this will be asked for NEET and JEE. Okay. So this is about the electric field due to dipole. Now we will discuss about electric field due to continuous charge distribution by using Gauss law. Okay. So next we have this question, that is state Gauss law in electrostatics and derive an expression for electric field due to uniformly charged infinite straight wire. So statement for Gauss law will be asked for 1 mark and derivation will be there for how many marks? 4 marks. So here statement I have already given, I will just directly tell you. It is the electric flux through the closed surface is equal to 1 by epsilon naught times charge enclosed. You can write the statement and write the formula, then directly you can move on to deriving the electric field. Then you can write some consideration, that is consider uniformly charged infinite straight wire, okay, of charge density lambda, and then consider the Gaussian surface, cylindrical Gaussian surface to calculate the electric flux or electric field as shown in the diagram. So let me draw the diagram here. So here I will consider a uniformly charged straight wire on which charge is distributed linearly and it extends till infinity, like this. Okay. Now if I consider this is the linear charge density extending till infinity, and I will consider a Gaussian surface around it. Cylindrical Gaussian surface. Okay. Let us consider here to here distance is r, electric field in the direction here is E, and if you consider some area, the area vector will be outwards. Area vector is outwards. If you consider here, area vector is upwards. This is the end surface. Okay, cylinder has 2 end surfaces and 1 curved surface area. Okay. Now the total flux through this cylindrical Gaussian surface, this is the cylindrical Gaussian surface, okay, this is the line charge or linear charge distribution, and lambda is the linear charge density. Total charge is q, you can consider inside it. Now total flux through the cylindrical Gaussian surface phi is equal to, what you can write, flux through end surfaces, let me write it as phi 1 plus flux through curved surface area, okay, I will write it as phi 2. Phi 1 is flux through end surface plus phi 2 is flux through curved surface, okay. Now that is equal to flux through end surfaces will be 0 because electric field is perpendicular to area vector, theta will be 90 degree, E into A into cos 90 degree is 0. So flux through end surface is 0 plus flux through curved surface, E into area of curved surface, I will write it as AC curved surface, so into cos 0 degree will be 1. So therefore total flux is equal to E into, what is the area of curved surface? Let us consider radius is R, length is L. So area of curved surface, curved surface area of the cylinder is given by 2 pi r, circumference 2 pi r into h, right? So 2 pi r, here height is L, so I will write it as L. This is equation number 1. Okay, this is equation number 1. Any doubt in this? Next, from Gauss law in electrostatics that we have just defined here, stated Gauss law, we have flux phi is equal to q by epsilon naught, that is given by lambda into L divided by epsilon naught. Lambda is a linear charge density. In the previous video I have explained lambda is equal to q by L, therefore q is equal to lambda into L. So from 1 and 2, can we equate this one is equal to this one, because phi is equal to phi, this one is equal to this one, right hand sides are equal. So E is equal to E into 2 pi r L is equal to lambda L by epsilon. L will get cancelled, so E is equal to lambda divided by 2 pi r into epsilon naught. So this is the expression for electric field. So in vector form also you can write, that is lambda divided by 2 pi r epsilon naught into n cap. Here electric field is inversely proportional to r. As the distance increases, electric field strength decreases. Write it down, make a note of it. You can pause the video and make a note of it. We have 2 more derivations, we'll complete them. Done? Shall I erase this? Yes. State Gauss law will be common. State Gauss law in electrostatics. So I will not write that this time. I will directly move on to the derivation. State Gauss law and derive an expression for electric field due to uniformly charged infinite thin sheet or plate. Infinite thin plate. So you can write this statement, then you can write some consideration like consider a uniformly charged infinite thin sheet with surface charge density sigma, which is equal to Q by A, total charge divided by total area, or dq by dA also you can write. So dq by dA also you can write, surface charge density. Okay, then consider two cylindrical Gaussian surfaces on either side of the thin sheet as shown in the diagram. So after that you can directly write, so let's consider this is the thin sheet, okay, on which charge is distributed uniformly. How? Like this. Okay, the surface charge density here is sigma. So let me consider Gaussian surface, cylindrical Gaussian surface on both sides, because this side also there will be electric field. Okay, so this side also there will be electric field, and this side also electric field. You have to take very thin sheet so that the charge is visible both sides. This side also, see, this is the charge. If I consider this side also it's visible, this side also it's visible. There will be electric field outwards in this direction, there will be electric field outwards. Half of the flux coming in this direction, half of the flux is going in this direction due to the same charges. If you take the thick plate, metal plate, the formula will be different. This is very thin plate. Okay, this is thin charged plate. This is the Gaussian surface. Gaussian surface. Okay. Now, if I consider the electric flux formula, electric flux through the Gaussian surface is given by, one is flux through end surfaces. Here area vector is in the direction of electric field. Here area vector is upwards. Angle will be 90 degree. Okay, therefore the total flux through the Gaussian surface is given by flux through end surfaces. So that is E into A into cos 0 is 1, and this end surface, this side also we have end surface, this side also we have end surface, plus E into A into cos 0 is 1, plus flux through curved surface area will be 0 because theta is equal to 90 degree. So flux phi is equal to E into A into 2 times is there, EA is 2 times EA. So this is equation number 1. Okay. Now from Gauss law, we have phi is equal to Q by epsilon naught. Okay. Since it is a surface, so we have surface charge density, that is sigma into A divided by epsilon naught. This is equation number 2. So from 1 and 2 we have, from equation 1 and equation 2, okay, so 2EA, which is equal to sigma A by epsilon naught, A get cancelled, so E is equal to sigma divided by 2 epsilon naught will be your answer. And this can be written in vector form also by considering 2 epsilon naught into n cap. Clear? This is the fourth derivation. Write down. Okay, shall I move on to the next derivation? Yes sir. Derives expression for electric field due to conducting sphere. Sir, what about non-conducting sphere, sir? That will come under special cases. I will do it or teach it separately. Due to charged, uniformly charged or uniformly distributed, recharged hollow sphere conducting solid or hollow sphere. The main thing is conducting. Why? If conducting sphere is considered, then the charges, all the extra charges resides outside the sphere, right? So therefore, if I consider here, you can write some theory. First you have to state the Gauss law, that is electric flux through the closed surface is equal to 1 by epsilon naught times the charge enclosed, that phi is equal to q by epsilon naught, where epsilon naught is absolute permittivity. So its value is 8.854 into 10 to the power minus 12 farad per meter, that you can write. If you want to write, you can write the value, otherwise just write the formula, then move on to consideration. Consider a sphere. Okay, so you can consider a sphere here. It is the three-dimensional one. Okay, consider a sphere on which charge is distributed. Uniformly. So all the charges resides on the surface of the sphere. Okay, so you can erase this, we don't want, but you should know this is the sphere. Charged, not ring, not the circle, it is sphere, three-dimensional one, just like a ball, sphere. So what I will do, I will consider a Gaussian surface around it, just like this, simple Gaussian spherical surface. Gaussian spherical surface. So let's consider the radius of the Gaussian spherical surface is small r. The radius of the conducting sphere is capital R. And if you consider the surface charge density, it will be sigma, and electric field is directed radially outwards. Yes or no? At every point, electric field is directed radially outwards. Now, if I consider the flux, total flux through the Gaussian surface, then it is given by E into what is the surface area of the sphere? 4 pi r square. 4 pi through Gaussian surface, 4 pi r square. This is equation number 1. Then from Gauss law, this is flux through the Gaussian surface. From Gauss law, flux, okay, from Gauss law we have flux is equal to charge enclosed divided by epsilon naught. What is the total charge enclosed? That is sigma into this area, not this area. This 4 pi r square is the surface area of the Gaussian surface, but Q is sigma into this area, 4 pi capital R square. So that's why I will keep it as it is. So from 1 and 2, you get E into 4 pi r square is equal to Q by epsilon naught. Therefore, E is equal to 1 over 4 pi epsilon naught Q divided by r square will come down. This is the electric field. Okay, where R is, where, let me consider this is A, R is greater than capital R. If R is greater than capital R, so this formula you have already studied, right? That is electric field due to point charge. That's why if R is greater than capital R, then sphere behaves as a point charge. Sphere behaves as point charge. I'll just write like this, point charge. Sphere behaves as a point charge when R is greater than capital R. Now, sir, what if I consider this Gaussian surface on the sphere? On the sphere, radius small r is equal to capital R. So, Gaussian surface decreases, comes to this one. So, electric field E is equal to 1 over 4 pi epsilon naught charge divided by, what is small r, is equal to capital R square. So, 1 over 4 pi epsilon naught. Charge is given by sigma into A divided by R square. A is 4 pi R square, area 4 pi R square get cancelled. Let me write it. So, sigma into area is 4 pi R square, that is the area of the sphere, divided by 4 pi epsilon naught into R square. So, R square 4 pi get cancelled. You will be having sigma by 2 epsilon naught. This will be the maximum electric field. So, E maximum is sigma by 2 epsilon naught due to sphere, that is on the sphere. Last one, it is inside the sphere. So, if you consider the Gaussian surface inside the sphere, if you consider Gaussian surface inside the sphere, what is the charge enclosed? 0. If charge enclosed is 0, flux through Gaussian surface is 0 by epsilon naught is 0. So, inside the sphere, that is R less than capital R, electric field will be 0, because inside the conducting sphere charge is 0. Okay. So, if you draw the graph of electric field versus distance, okay. So, till some radius R is equal to capital R, electric field will be 0, and after that it varies like this. This is the maximum electric field given by sigma by 2 epsilon naught, and after that E is inversely proportional to R square, outside, on, inside it is 0, on it is maximum. So, outside inversely proportional R square, you will get a graph like this, it extends till infinity. So, these are the 5 derivations which you have in second PUC electric charges and fields chapter. Hope it is clear to you. Okay. If you have any doubt, you can just comment me in the text me in the comment section. I will try to clarify the doubts in the next coming videos. Thank you so much. Keep supporting. If you feel the content is useful, please share it to your friends. Thank you.